Continuity at a number and on an interval. Our objectives in this lesson is to use the definition of continuity to determine whether a function is continuous at a number and intervals on which a function is continuous. Also, to use properties of continuity. Let's begin with the definition of continuity. Now, it's very important that we know and are able to use this definition anytime we are trying to figure out or prove if a function is continuous. A function f is continuous at a number c if the following three conditions are met. Notice that it is all three conditions that must be met. First, f of c is defined. Another way to say that is c is in the domain of the function f. We can think of this by thinking that there is no hole, graphically, or that the function value exists. These are other ways to think about it, but we want to remember it by thinking f of c is defined, that part that we highlighted right there. Next, the limit as x approaches c of f of x exists. So often, continuity is destroyed when the limits from the left and right don't equal each other. So we want to make sure that the limit exists, which often means making sure that the limit as x approaches c from the left for f of x is equal to the limit as x approaches c from the right for f of x. So the two sides are approaching the same place. Another way to think of this is that we have no jumps. But again, it's important we remember it this way that we highlighted. The limit as x approaches c of f of x exists. That's how we'll write it. That's how we'll think of it. And finally, the two above equal each other. The limit as x approaches c of f of x equals the f of c value. So the limit equals the function value. Another way to think of this is that the function gets where it's going. Remember that the limit is all about where the function is going, but it doesn't necessarily have to get there. So here we're thinking that the function gets, that's this part, its function value, where it's going. The limit is all about where the function is going. But again, we think of it that way that we highlighted it. The limit as x approaches c of f of x equals f of c. If any one of these three conditions is not satisfied, then the function is discontinuous at c. So it's important that all three of these are satisfied. Graphically, we can think about continuity. So just as a quick check to know that the function is continuous is that we think about the fact that we can draw the graph without picking up our pencil. I'm going to abbreviate without, like that, picking up our pencil. So that's a quick check graphically. Not the formal definition, because of course we are using all three of these exactly how those are written. Now let's talk about what it means for a function to be continuous on an open interval and continuous on a closed interval. So a function is continuous on an open interval, a to b, if f is continuous at every number in that open interval. Now notice the way that this is written here. The limit as x approaches a from the left of f of x does not equal f of a. So if we think about what that looks like, if we have an endpoint a the function approaching it from the right heads to a value, but there is a hole at that value. And the limit as x approaches b from the left of f of x does not equal f of b. That means coming from the left, the function is headed to this spot, but it does not get there, and that's at b. And that's why it's the open interval. It does not reach these two endpoints, a and b, but the function is continuous at every number inside that interval. Similarly, we can talk about how a function is continuous on a closed interval, meaning we're including the endpoints a and b, if the function is continuous on that open interval, but also continuous from the right at a and continuous from the left at b. So notice these were not equal to the function value. These are equal to the function value. So the difference in how continuous on a closed interval looks is that the function gets where it's going to both of those endpoints of the interval, a and b. Now there are types of discontinuity. We have the removable discontinuity. You're going to think of those as holes. A number c at which the function is discontinuous at c, but the limit as x approaches c of f of x exists. So you might think of it something like this. Both sides head to a place, but the function value does not exist, or the function value exists somewhere else, such as above or below where that hole is. Now, the discontinuity can be removed, which is why it's called a removable discontinuity, by defining or redefining the value of f at c to be the same as that limit, which means we redefine that function value so we can fill in that hole, and then the function will be continuous. We also have non-removable discontinuity, where we cannot remove the discontinuity, such as a vertical asymptote or a jump. In fact, we often call non-removable discontinuities jump discontinuities because we see those most often. For example, the function heads to one place from one side, but to another place from another side. That would be an example of a jump discontinuity. Let's take a look at some examples. First, use the graph of f of x shown to answer the following. And here's our graph of f of x. Part A, determine if f is continuous at c. B, if f is discontinuous at c, state which conditions of the definition of continuity is or are not satisfied. C, if f is discontinuous at c, determine if the discontinuity is removable. And finally, D, if the discontinuity is removable, define or redefine f at c to make f continuous at c. We'll look first at c equals 0. Going to our graph where the x value is 0, looking in that area, I do a quick check to notice, can I draw the graph through 0 without picking up my pencil? And I absolutely can. So to answer part A, f is continuous at c equals 0, at the x value 0. So we have determined that the function is continuous, so parts B, C, and D don't pertain to this value. How about at c equals -4? I go find where the x value is -4, and I notice there is a jump. Part of the function comes down here, part of the function goes up there. So I know right away that f is not continuous, or I could say f is discontinuous at c equals -4. Now we have to go through and state which condition of the definition of continuity is not satisfied. Let's do a quick recap of what we learned we have to have for a function to be continuous. So we have to have that f of c is defined, the limit as x approaches c of f of x exists, and those two things equal each other. Well, when I look at this problem, the first part, f of -4, does have a value. That function value is right there at -1, -2, -3, -4, -5. That function value is defined. So that's not the part that fails. The part that fails is that the limit does not exist. So I'm going to write that the limit as x approaches -4 for our function f of x does not exist. So I already stated, part A, the function is discontinuous at this x value. Part B, I've determined which condition of the definition of continuity is not satisfied. Determine if the discontinuity is removable. Now that would be if we could simply fill in a hole and make the function continuous. We cannot do that here. This is a non-removable discontinuity because we have a jump discontinuity. And finally, we can't do part D because the discontinuity is not removable. Let's take a look at when c equals 3. So over here, that's the x value 3, and I notice all of this stuff going on where x is 3. So first of all, I cannot draw this without picking up my pencil. I'd be coming from the left, I'd have to stop, plot that point above, and then go back down to the line and keep going. So part A, I know that my function is discontinuous at c equals 3. Now, which condition of the definition of continuity is not satisfied? Do I have a function value? Yes, I do. F of 3 equals -1. So that part is fine. Do I have a limit? I do. The limit as x approaches 3 of f of x does have a value. Notice both sides head towards the y value -2. So that one is also satisfied. What is not satisfied is that the limit and the function value are not equal to each other. So the limit as x approaches 3 of f of x does not equal f of 3. That's the one that fails. Now we need to determine if the discontinuity is removable. And in fact, yes it is. I can simply fill in this hole with the proper function value and it will make the function continuous. I'm going to undo that so our graph isn't messed up. But it is removable. Therefore, I will be able to redefine the function to make f continuous at c. So part D, I'm going to redefine this function value. I want the function value not to equal -1 because then it's not the same as the limit. I want it to equal what the limit is, which is -2. That way, it would fill in the hole. Next example. Determine if g of x equals the rational function x squared minus 9 divided by x plus 3 is continuous at the numbers c equals 0 and -3. If g is discontinuous at c with a removable discontinuity, define g of c so that g is continuous at c. So anytime that we're trying to determine if a function is continuous, we want to remember the three parts of our definition of continuity. So let's jot those down. F of c is defined. the limit as x approaches c of f of x exists, and then those two things equal each other. The limit as x approaches c of f of x equals f of c equals. It's very important that we think of it exactly like that every time we're talking about continuity, so we might as well jot it down. Let's begin by looking at c equal to 0. So for c equal to 0, is f of 0 defined? Well, first of all, our function is not called f, so let's back up a sec. Is our function, which is named g of x, is g of 0 defined? Well, if I plug in 0, what do I get? 0 squared minus 9 over 0 plus 3. That makes negative 9 over 3, which makes negative 3. Yes, it is. Our function value is defined. Next, does the limit as x approaches 0 of g of x exist? Does it have a value? Well, let's take a look. Can I do direct substitution? 0 squared minus 9 over 0 plus 3 equals negative 3. Of course I can. I just did it in the previous one, and the limit exists, and then clearly those two values equal each other, so the third part also exists. The limit as x approaches 0 of g of x equals g of 0. Therefore, all three parts are satisfied, and I can say, therefore, g of x is continuous at c equals 0. All three parts of the definition are satisfied. Now finally, let's take a look at c equals negative 3. Let's begin with g of negative 3. If I try to plug this into the function, negative 3 squared minus 9 over negative 3 plus 3. Well, I notice right away that the denominator is 0. Negative 3 is not in the domain of the function. Therefore, the first part of the definition of continuity fails. It is not satisfied. So just because of that first part, we can say g is not continuous or discontinuous at c equals negative 3. So if g is discontinuous at that value with a removable discontinuity, can we define g of c so that g is continuous at this value? Well, let's take a look if we can find the limit. The limit as x approaches negative 3 of x squared minus 9 over x plus 3. Well, we already know that substitution is not going to work. Our denominator is 0, negative 3 is not in the domain. But we know from previous practice with limits that sometimes we can manipulate a function with factoring. And in fact, we can do that with this one. So let's factor the difference of squares in the numerator. And we have a common factor. And now substitution will work. I can plug in negative 3, and negative 3 minus 3 gives us negative 6. So we do have a limit. We just need our function value to equal what that limit value is. So we can define g of negative 3 to equal negative 6. And then our limit value will equal our function value. In this example, we will determine whether the function h is continuous at 2. So remember, we see continuous and we think of our three parts of the definition of continuity. The function value is defined. F of c is defined. The limit as x approaches c of our function exists. and those two things equal each other. The limit equals the function value. Now, just to help us out here, let's remember that our function is called h of x. So we can replace all of these with h to help keep us on track, calling our function h. And let's start with the first part. Is h of 2 defined? H of 2, notice I have only this piece that has the equals, so I plug it in there. 3 times 2 minus 1 does give us a value, 5. So there is a function value. Second, does the limit exist? Well, because we've got the left piece and the right piece, we need to check both-sided limits. Let's start with the limit as x approaches 2 from the left. In order to do that, we're going to use this left-sided piece. So this will be equivalent to the limit as x approaches 2 from the left of 3x minus 1, and substitution will work here. We get 3 times 2 minus 1, which is 5. Now let's check the limit as x approaches 2 from the right. We're going to use the right-sided piece of the function. So that's going to be equivalent to the limit as x approaches 2 from the right of the expression x squared plus 3. Using our direct substitution into that expression, we get 2 squared plus 3, which makes 4 plus 3, or 7. Now I notice that this left-sided limit 5 and this right-sided limit 7 are not equal, since the limit as x approaches 2 from the left does not equal the limit as x approaches 2 from the right. The limit does not exist. The limit as x approaches 2 of our function does not exist, which follows that h of x is not continuous at 2. Or we could say h of x is discontinuous at 2. What type of discontinuity? Well, if one side is going towards the y value 5 and the other side is going towards the y value 7, that is a jump discontinuity. Are those removable? They sure are not. These are non-removable because we can't simply fill in the hole and make it a continuous function. Finally, let's talk about the properties of continuity. Basically, any combination of continuous functions makes continuous functions. Let's make that shortcut note. Any combination or combo of continuous functions makes continuous functions. That's the shortcut way to think about it. You multiply a continuous function by a value, it's still continuous. You add or subtract two continuous functions, they're still continuous. You multiply two continuous functions, makes a continuous function. You divide two of them, as long as the denominator is not 0, you get a continuous function, and you do the composition of two continuous functions. You still get a continuous function. The following functions are also continuous when we put together continuous functions. So just quickly to look at an example of that, which of the following functions are continuous for all real numbers x? Are continuous. That's all we have to determine. Well, I don't know about you, but this function right here, I don't know what that looks like, but I do know what the functions that make it look like. Y equals e to the x. We know what that looks like. That is a continuous function. How about y equals x squared? We know what that looks like, and we know that that's a continuous function. How about y equals sine x? Again, We know what that looks like, and that is a continuous function. So adding or subtracting continuous functions yields also a continuous function. So even though I might not know what that sum is, I do know that the parts are continuous, so together it makes a continuous function. How about the next one? Y equals 3x. Again, linear. I know what that looks like. Next to it is a composition of continuous functions. I know that y equals square root of x is a continuous function. That's my rainbow function, looks like that. And inside it, I have that parabola, y equals x squared plus 7. Again, y equals x squared plus 7. Quadratics are continuous functions, and that's a composition of continuous functions. So again, this is a combination of continuous functions, therefore it has to be continuous. Now the last one, secant x. I may not remember exactly what it looks like, but I do know that it's made from 1 divided by cosine x. And because cosine x is able to equal 0 at some parts, I'm going to have a discontinuous function here. So this one is not one that we would choose. Hopefully you have a hang of continuous functions. Thanks for watching.